AP Physics C Mechanics, Problem 1998 M2, Rotational Motion. Part A is a simple momentum kinetic energy problem with no rotational motion. Part 1 asks you for the total kinetic energy after the collision. You can equate the initial kinetic energy of the system to the final kinetic energy, but you still need to find the final velocity. You can equate the initial and final momentum and solve for Vf. The total kinetic energy of the assembly turns out to be mvo squared over 6. Part 2 asks you for the change in kinetic energy as a result of the collision. The kinetic energy we found in Part 1 is the final kinetic energy, and to find the change in the kinetic energy, you need to subtract the initial kinetic energy of the single lump from the final kinetic energy. The answer is negative mvo squared over 3. Part B has rotational motion. Part 1 asks for the center of mass of the assembly, which is the rod with all three masses, using the sum of the products of the masses and their distance from the point of interest, all divided by the total sum, which will get us the new center of mass, which is 2/3 L from the left. Part 2 tells you to indicate the direction of the motion of the center of mass after the collision. Conceptually, we know it will move in the same direction that the single lump was going. Part 3 asks for the velocity of the center of mass. Once again, you equate the initial and final momentum and solve for Vf. Now we have to find the angular velocity of assembly. We have to equate the rotational momentums. Li is the momentum of the single lump times the distance from the new center of mass to the point of its collision. Lf is the moment of inertia multiplied by omega, which is what we're trying to find. I is equal to the sum of the moments of inertia of the left and right sides of the assembly. Once you plug in and simplify, you should solve for omega and get VO over 2L. For part 5, you have to determine the change in kinetic energy due to the collision. You will need Vf of the center of mass, the I of the assembly, and its angular velocity to solve this. We found these values previously. The change is equal to energy final minus energy initial. Energy final is the sum of the final vertical energy found in part 1 of part A, now labeled EFH, and the final rotational energy, I omega squared over 2. Once you solve, EF should be mvo squared over 4. E initial is simply the kinetic energy of the flying lump. Plug in the values, and the difference should be negative mvo squared over 4 joules.